In this video, I'm going to show you the basis for conducting an EMI project review for your printed circuit board layout, and in this case is a motherboard design which includes an all-winner A64 processor, so we're talking about a complex design, and we're going to see on what we should focus on as EMI specialists if we want to give this board the best EMI performance. So let's jump straight into the product review. So the first thing that I usually do when doing an EMI review is to make sure that the stackup is correct. And this is the first thing which gives you already 90% of the EMI performance. So why is that? Because the stackup tells me how the fields are contained within the PCB. So what do I mean by that? By that, I mean that the layers always go in pair when we're talking about PCB design. And this means that if I have a layer where I have the signals, then automatically, and this should go even without thinking, then I have a return reference plane adjacent to it. So what does it mean adjacent? It means that the return reference plane, which is also called in short RRP, should go either above the signal layer or below the signal layer. But it has to be as close as possible so that it does its job, which, as the name implies, it has to give the path for the return current to flow back to the source, but also it has to give the reference potential for the signal layer. So if we don't have this scenario, then we are most likely going to have problems in terms of EMI, but also in terms of signal integrity. And this is because the electromagnetic fields are then allowed to grow bigger instead of being contained within the stackup. So when we place the return reference plane as close as possible to the signal layer, the electromagnetic fields stay smaller. And one of the things that I would like to emphasize in here is that the power layer is not as good as the return reference plane, because when the current has to return back to the source, it has to cross from layer to layer until it is finally able to close the current loop and reach the source being that originated it. So what does it mean? It means that it has to cross the space in between the layer, which still has an impedance, and this means that if a current flows through this impedance, it will create a voltage drop, which creates the noise in between the stackup. Now this noise then can cause a crosstalk between the signal transition layers, and it can even cause emissions from the edges of the board. So I don't recommend using the power plane as a return path, especially when you have high-speed signals. And I know already someone might have told you that you can use the capacitors, but the problem is that the impedance of the capacitors at high frequencies will also be inductive. So this means that the portion of the return current with the high frequency will not flow through the decoupling capacitors, and it will actually flow through the layers in the form of the displacement current. But this also means that there will be the displacement current spreading in between the layers, trying to find the path of this impedance so that it can go back to the source and close the current loop. The low frequency portion of the current flowing through the decoupling capacitors instead will often make a larger loop, which in turn creates common mode currents, which then can create emissions. So we don't use the forward layers as a return layer, or at least I don't use it anymore, and I don't recommend you either. So the first thing that we want to do is check the stackup of the board. Okay, so we can immediately see that the stackup is composed of 6 layers. So I would expect to see at least 2 return reference planes, because I want to see that each signal has a return reference plane adjacent to it, or at least the one side of it where it can couple to it. So there could be a few ways that this stackup could work effectively. And when I say effectively, of course, I mean in terms of EMI and signal integrity here. So the first one is that if we have the layer 1 with the signal and power, which is paired to the return reference plane on the second layer. Then the third layer has a signal and power as well, paired with the return reference plane on the second layer. And the remaining layers, so the layers 4, 5, and 6, will then be the mirror image of the first 3 layers. So this means that we're going to have layer 4 with signal and power, which are paired with layer 5 as a full return reference plane, and layer 6 also paired with the return reference plane on layer 5. And we can do this because of the skin effect, which allows us to have the return current from layer 1 on layer 2, where the return current from layer 1 is only on one side of layer 2 and does not mix with the return current from layer 3. And the same situation we have from the return current of layer 3 on one side of layer 2. This, of course, will mean that the skin depth calculated for the signals that we have allow us to do that. And in this case, we have two different return currents without creating crosstalk between them because of the skin effect. And the same we can apply to layer 5, which is the return reference plane for layer 4 and layer 6. And so here, when I say signal and power, I intend both of them routed with tracks and not as planes or large copper cores. So with this kind of stack up, we will then have 4 layers for signal and power that we can use. So it could be a cheaper stack up. In this case, though, we want to be careful that layer 3 and layer 4 are not interfering with each other. And this is also why it's a good reason to have one thicker dielectric layer in between them. The other type of stack up that could work effectively here is where we have layer 1 as a signal paired with layer 2 as a return reference plane. And then in the same manner, we will have layer 6 as a signals paired with layer 5 as a return reference plane. And then we can use layer 3 as a plane for the power and layer 4 as well as a power plane. So in this way, we can increase the amount of current that we can deliver. The other type of stack up that we can use is a combination of the two I just proposed. So where we have layer 1 and layer 6, which are used for signal and power. Then layer 2 and layer 5 are used as a return reference plane. And then layer 3 and layer 4 can be used either as a signal or power, and they don't need to be of the same type. So layer 3 can be signals, and then layer 4 can be power, or vice versa. And as a general rule, we have to always think at assigning the layers in pair, so not as single layers. This means that the pairs, they have to be signals and return reference plane, or power and return reference plane. So no matter what kind of combination you mix of the plane, just make sure that each time you have a signal or a power plane, have also a return reference plane adjacent to it as a pair with the other signals. Any other version which differs from this is going to create some antenna-like behaviors and are not going to give us a good results in terms of EMI, because the electromagnetic fields will start to spread around. Okay, so now let's examine the layer arrangement and perform an analysis to ensure that the stack-up does not introduce potential EMI issues. So the first layer is dedicated here for components and for signal routing, as well as some power. So this is a typical choice. And as I mentioned before, the second layer had to be the return reference plane. So let's see what has been used in here. So great, this is exactly what we should expect. With this configuration, we have the completed pair for layer 1 and layer 2. Also see how this layer is a full solid plane where there are no splits or cuts or large gaps. So the signals on layer 1 always have the return reference plane under it through the whole propagation of the signals. And so in this case, if you take any trace on the board and check for each point along the trace to make sure that there is a good return reference plane underneath, you will see that there are no impedance discontinuities. And this is important because it keeps the signal consistent and prevents the problems like reflections or unwanted emissions that can happen when the impedance changes. Let's see now for layer 3. This time we have also some digital signals in here. So this is still good because now signals on layer 3 are paired with the return reference plane on layer 2. Now let's see layer 4. Okay, so here's where most of the routing has been done, and we have many digital and power signals here. Plus we have also large chunks of copper field, which are connected to this GND net. Okay, so far so good. Now, as I explained before, the layer 5 that I should expect to see here is another return reference plane to which I compare the signals on layer 4. Let's see what they have chosen here. Okay, this is not that good, because here we have a mixed power layer. So we have a big copper area for the 3.3 volts, and then we have also other voltages, either in traces or in polling fields. So we know already that this is not going to be good for us. But let's see the last layer that we have, which is layer 6. So this is also dedicated for digital signals and power, plus a large copper area for the GND net. Okay, let me explain the problems of this choice of having the power layer in layer 5, as I was mentioning before. So the problems here are two, and this is why this plane is not good to provide a path for the return current for layer 4 and for layer 6. So the first problem is that we have the signal crossing the split horizontally. So this means that there will be parts of the signals where there is no plane under it. So this is a problem called impedance discontinuity. And what it simply means is that the signal reaches the split, but then its impedance changes, so also the signal changes, and we will have reflections. The second issue is that the return current from layer 4 and layer 6 that is now flowing in layer 5 has still to go back to the source that originated it to close the current loop. But layer 5 is not connected to layer 2, which is the return reference plane, and the zero voltage potential for the signal. So this means that the return current has now to go from layer 5 to layer 2 somehow. But the question is, how is it going to go from layer 5 to layer 2 if there is not DC connection between the two layers? So remember, layer 2 is the GND net and layer 5 is power. So if there was a DC connection between the two, then this will be a short circuit. So in our case, this means that cannot be a return current between layer 5 and layer 2 unless there is an impedance to it, because otherwise this would be a short circuit. So the way that the return current is able to go back from layer 5, which is power, and then layer 2, which is the 0 volt potential, is through the capacitance between these two planes. So this is either through the decoupling capacitors that we have between layer 5 and layer 2, or by the internal capacitance in between the layers. This means through the displacement current. As I mentioned before, the problem with the conduction current flowing through the capacitors is that the impedance of the capacitors will be low only up to the resonant frequency of the capacitors. After this point, the impedance of the capacitors become more and more inductive. The low frequency portion of the current flowing through these capacitors form a larger current loop, and these will create the common mode voltage sources, which are big issues in terms of emissions. The remaining current that has to go back to the source, so this is the current that goes as displacement current, now has to flow through the dielectric in between the layers. This means that it will spread to find the path of least impedance to go back to the source, and when it crosses the dielectric between the layers, this dielectric have also an impedance. Otherwise, there will be no current, as we know. So this means that the current flows through this impedance, and this will generate a voltage drop in between the layers. So this voltage drop will be noise in between the layers, and it can also create emissions from the edges of the board. What this means for us is that this can create EMI issues, but also signal integrity issues, because this noise is also going to couple with the other signal that transition from one layer to the other layers with the other vias. So this is why, like I said previously, we don't want to use the power plane to provide the return current to the signals. And this is why I said that the only pairs allowed are the signal and return reference plane and power and return reference plane, where the return reference plane is the reference plane for the signals. Because, like I said, we want to maximize the containment of the fields. So the signal area has to be paired with the return reference plane, and the power plane has to be paired with the return reference plane. So the stackup that we have here should be changed to one of the versions that I mentioned before in order to remain a 6-layer board. The problem with that is that I will have to modify the entire layout of the board. So usually at this point we can already discuss it with the client what we can do about it and what option can they go with depending on the timeline of the project. And this is also why it is super important to understand the impact of EMI before we even do the layout of the board. What are the other options that we have? The other option would be to introduce more return reference planes to match the needs of the signals and power layers. But this will mean increasing the stackup of at least 2 more layers. So we will have an 8-layer board. And as I said, the options here are mainly 2. The option 1 is that we keep 6 layers, but we try to route the board differently. And we'll make sure that layer 5 is a return reference plane instead of a power layer. And the second option, we add 2 more layers, ideally 2 more return reference planes, but we go for an 8-layer board. So option 1 is the one that takes longer time because it requires a rework of the layout. So this means extra engineering cost. However, if done correctly, this means that the board will stay a 6-layer board and we will have the expected price for the production. For option 2, instead, this is the fastest because we can probably make a very small modification of the layout at this point and we still have a solid stack up in terms of EMI. This option though will probably increase the cost of the stack up, so this price needs to be accounted for also during the production. And so if we use the second option, we can then place a return reference plane between the layer 6 and the layer 5 to provide the return path for both of them. And then the other return reference plane, I will probably position it between layer 5 and layer 4. And doing so will allow me to have a closed return reference plane for layer 4, which is master digital signals. So as an EMI specialist now, our job will be to present this information to our clients or also to the project stakeholders if you are working for a company. But what the important thing here is that we can present the problems in terms of EMI so that we can choose the best strategy for the project. Okay, so now that we have reviewed the stackup, we will take a look at the layout itself. And at this point, we want to make sure that there are no other visible issues or anomalies in the layout. And by the way, if you're interested in becoming an EMI specialist yourself, you can head over to our website at fresioelectronics.com, where you will find details on how to apply to one of our exclusive programs designed to help you do exactly that. So the first thing that we're going to check now is for antenna-like structures. And I see here already something that I'm not particularly fond of, which are these copper pores on the way that they have been used. And this is because I can see that there are antenna-like structures that can create emissions problems. So what do I mean with antenna-like structures? For example, the floating copper islands. So if there are copper areas not properly connected or not connected at all, they can act as a small antenna. And these floating patches then can pick up or radiate the signals, which then will cause EMI. Also, when they are connected but not sufficiently, this portion of the copper fields will still act as an antenna structure. And this is because depending on the frequency of the signals that couples to it, these signals can produce voltage drops through the parasitics of the copper field. And then they will act as an antenna. And the same we can say also for long traces with no return path, when these traces stretch over a long distance without a nearby return reference plane, which then can behave like dipole antennas or radiating energy into the environment. So another example is to have stubs or branches, and sometimes the designer leaves this portion of traces branching off the signal lines. And this means then that the traces are split into different branches, and these stubs can then reflect the signals and then radiate them acting like an antenna. So the other problem that we're going to look at is the slots or gaps in the return reference plane. But these we already covered in part during the stackup analysis, so we will not go much further with this problem here because we will make sure that this issue is solved by selecting the right stackup proposed before. So with the full return reference plane, with no splits or cuts. And in general, when doing the EMI review, but also, and I would say most importantly, during the layout of the board, we have to think in terms of electromagnetic fields and frequencies, especially how the parasitic behavior of the layout will change as the frequency of the signal changes or with its harmonics. So it's not just about the main frequency of the signal, but also about the harmonics within the signals. So let's start the analysis on the layer 1 first. So the first thing that I would recommend here is to get rid of this copper field or copper pores. But before you do that, make sure that you have a copy of the project where you're doing the modifications like I'm doing in this case. And what I want to do here is I want to delete the copper pore, first of all to get rid of the antenna-like structures I mentioned before, but also to see if the nets used for the return current and reference, which is typically the GND, has the pins and all this connection made with the lowest inductance possible. So this means that I want to see if the GND vias are placed as close as possible to the pins and the pads of the components. And also notice that by removing the copper field, I have now much more space for the routing of the traces. Now, when I look at the GND net, we see that there are many points where the vias could be placed much closer to the pads. And what this will do is reduce the inductance to the return path, because now the current will be much closer to the return reference plane. And we have to remember that the common mode currents are generated because we have these parasitics. So reduce this parasitic inductance, which will also help us in reducing the common mode currents. And especially points like this one here, what we can do is to add more vias to connect the return reference plane and to place them closer to the pads, instead of also sharing them with other pads. So for each GND pad, we want to make sure that we have at least one via which connects straight to the return reference plane. The other improvement that I will do is to get rid of the small traces connected to the GND vias. And I will also remove these stitching vias that we have here on the board, but what I will do later on is to add them again in a more strategic way so that we can make sure that these vias are actually doing the work that are supposed to do, which is to contain the field. So in this case, I will make sure that I create a sort of a Faraday cage to contain all the fields within the board. But what this would also allow to do is to make sure that the return reference planes have as many points of contact as possible so that they are equipotential with each other. The other benefit that this will have is that I will have more return and reference points on the vertical axis for when the signal transition from one layer to the next through the VS, so that the fields are contained not only when they propagate horizontally with the traces and the return reference plane, but also when they propagate vertically with the VS. And this is a very important point that leads to so many EMI problems, because often the signal do not have the return and reference VS next to the signal VS, and this leads to having the fields uncontained and spread through the stack up of the board between the layers, which then couples with other traces and cables and eventually find a path to radiate out of the board. The other very important point that I see here is that we do not have a single return reference plane, which in our case is the GND net, so the ground net. But what I see is that the return reference plane is divided into multiple nets like the GND, GNDA, and there are a few others. So what I need to do is first to check if these nets require an isolation by safety requirement. But if this is not the case, like in here, then we have to change all these GND nets to a single return reference plane. And this point is super important, because if I split the return reference plane, this one that everybody calls ground, all this will create is the voltage difference between the return path of the signals, which will in turn create common mode current noise. So don't use the word ground, which is very confusing for you. And also it doesn't have any meaning in terms of EMI. What I suggested to use in here is the return reference plane, so RRT instead of GND, and unify all these nets, so the GND, other GND nets, into one single return reference plane, so into one single net, which is the RRP. So my job from here forward would be to change all these nets into a single net and to add also the vias as close as possible to the pads so that they can connect with the lowest impedance possible to the return reference plane, which will be placed adjacent to the signal layers. So now the next and most important thing that we can check at this point is the chances of having crosstalk between traces. So this means that we have to check that the traces have enough distance between each other so that the signals of one trace does not couple with the other one. And we can start the review by selecting one corner of the board, and then we move down and then on the side. So we are not going to run a simulation of the layout at this point because it is a bit out of the scope at the moment for the project. What I want to give you is instead an overview of the process that most boards require, rather than the special cases that need to be backed up by the simulation. And I mean, there are definitely those cases where you need to simulate the board to make sure that the signal integrity aspects are respected, especially because in many situations the signal integrity aspects are related to EMI. We are really not going to get into these right now, because what we're looking for at this point is to have a general rule of thumb respected. So the rule is very simple here. Each signal trace that is not routed as a differential pair should be routed at least 2 to 3 times the width of the trace distant from another signal trace. So this is a general rule of thumb, and this means that not in all the cases this is going to be an asset over crosstalk, because there would be some cases where we need to be more careful, but at this point we just want to make sure that all the traces are starting from a good reference point. So what I'm going to do now is I'm going to take a look at each layer and see where there are some traces that are routed closer than 2-3 times the trace width to other traces. For example, I can see that in here the traces are routed fairly close to each other, and so what I want to do in this case is to space these traces further apart from each other so that when the signal is propagating in one of these traces is not also coupling to the other traces and generating noise. So this is a thing that happens very commonly when you have the situation, for example, that your board freezes or an interrupt is triggering unexpectedly to when you have some sort of ghost signals. This is usually one of the most common phenomena that triggers this situation. And especially when you route reset traces close to faster signals, or as in this case, a wake-up signal close to the communication protocols. So wherever we can, we are going to increase the distance between the traces and use the real estate space available off the board as efficiently as possible in terms of electromagnetic fields. And the same process we're going to use on all the layers of the board. So this is not just for the first layer, but on all the layers of the board. Okay, now the other point to which we need to check is creating the stubs of branches. And what this means is that we want to make sure that each connection is made as a point-to-point connection and that the signal trace does not split into multiple parts. And if they're splitted, we want to make sure that this connection is very short. So let's take a look at the example of these traces in here. So here we have a signal which starts at one of the pieces of the BGAs, and the signal is divided into two sections where the via divides the net into two branches. So one part that continues to connect the resistors on the right-hand side, and the other part of the net continues with the vias. And then we have also a signal trace on layer 4. So what happens here is that the signal arrives at this point and its impedance suddenly changes. And depending on the signal that you have and depending on the impedance change that the signal sees, these will create the reflection. We want to make sure that even if these are pull up or pull down resistors, these stubs are short as possible. So we don't want to create the branches. So we want to make sure that these resistors are closest to their BGA. So that in this case, the stubs between the via and the resistor is much shorter. Or we want to simply place the via as close as possible to the resistor, so that the transition between layers does not make this branch between the pull-up resistor and the vias. Now, may we point out that this is simply a pull-up resistor, but it doesn't really matter because what we're creating here is this antenna structure, and especially let's suppose that this is a I2C connection, then we will still have some fast transition of the signal from low to high and from high to low. So what it matters is the frequency of the rise time of the signal and the fall time. So this is the frequency that we're talking about, the frequency of the harmonics which create this signal rise and fall time. So what it really matters is the speed at which the signal transitions from high to low and from low to high, because the harmonics contained in the signals have different frequencies there than the main frequency signal that you're talking about. So this is a problem and this can cause a signal integrity issue, but also what can happen here is that the reflection then decouples to other traces or structures overboard, and then they will create emission. So this is not a direct emission maybe from the traces. Because of the reflection that we have within this trace, this reflection can then couple to other signals and then find the way to propagate. Or what else can happen is that the signal, depending on the energy of its harmonics, can also start resonating along this traces segment and again cause the emissions. So whether this is directly or not directly, the signal can couple to the traces, and so we want to make sure that we avoid this, making these connections like that, and when extremely unavoidable, like I said, then we want to make sure that the stars that we create are super short so that the frequency necessary for creating a resonance of the trace is very high, and the one frequency that is going to hit the resonance has a very low energy. So this is another point that needs to be corrected or at least improved in this board. Okay, so the next point that we're going to cover is the length and matching part, or at least the part that we are more interested in, which is about the crosstalk coupling, and also on how it improves a bit more these bumps so that we can get less energy dispersion, resonances, and also crosstalk. So not only with the other signals, but with the same traces too. And one of the things that I would like to point out is that the traces here are quite close together. So we want to improve the distance between the traces first. Then the other point that I would like to briefly touch on is the style of the so-called length and matching. So perhaps more important to recognize that to those who are new to the high-speed routing is that rather than doing the length matching, we have to do the time matching. And this means that we have to make sure that the timing is right and not the length. Because in fact, the problem with doing length and matching instead of time matching is that if we were to compare a signal routed on an outer layer and a signal routed on an inner layer, the speed of the signal, so the speed of a propagation using the same length trace is going to be different. And this is because the fields on the signals on the outer layer will also propagate on the air, and the fields of the signal on the inner layer are going to propagate in the dialectic between the layers. And this means that having the same trace length does not mean having the signals propagate with the same time. So although there is the same length, one is going to be faster and the other is going to have some delay. Also, what changes between routing on an outer layer, so a microstrip, and on an inner layer, so a strip line, is the fact that the crosstalk is going to behave differently. Because in the case of the microstrip, we're going to have the effects of the far end crosstalk and the near end crosstalk, but on the strip line, we are are not going to see the effect of the firing crosstalk. And so this is also one of the reasons why it is typically better to route the high-speed signal on the inner layer rather than on the outer layer. Also, another benefit of routing high-speed signals in the inner layers is that the energy of the signals and the emissions from it are then better contained when routed internally than externally, because we have this return reference plane which contain even more the fields, whilst if you route it on the outer layer, you don't have this return reference plane on the top of it, so the fields are then propagating a little bit more in respect to the one routed internally. So this is something that we want to keep in mind. However, the improvement that we want to make in here is, first of all, to have the time matching instead of the length matching, but also to have the serpentine with smaller bumps, and they have to be also more frequent. And what this will do is that it will increase the resonant frequency of the structure, and this means that the frequency that is going to resonate in the structure and create issue is going to be shifted at a higher frequency, so farther away from our signal boundary. But also what is going to happen is that there is going to be less crosstalk between each of the legs of the serpentine, because the length with which the signal couples is going to be less, so there are less fringe fields that are going to be coupling to the other portion of the trace. This is perhaps one of the best points to mention, that we need to think in terms of frequency domain when we are doing the EMI review, and not only in terms of time domain, because digital signals, as we know thanks to the Fourier transform, are composed by many signals with different frequencies and harmonics. So to come back to the serpentine, a general rule of thumb is that we want to space the bumps, these bumps of the serpentine, at least 3 to 4 times the trace width, and then the serpentine should have smaller bumps and more often. So this means not fewer and larger bumps like we have in this case in here, but we want to have smaller and more frequent. And so depending on the signal, of course, we might have to simulate this and actually calculate if we need to have better and accurate values. So the next step that we want to cover, although we are just going to cover it briefly here, is the control impedance. I just want to mention this because I remember I did not give much of importance when I was testing out, but it is perhaps one of the most important things that you can do. To design the traces with the controlled impedance simply means that you want to have the traces designed in such a way that the impedance between the signal trace and the return reference plane is constant. And the way that we typically do this is by making sure that the width of the traces is constant throughout the whole length of the trace. So to calculate this impedance, this can be done with calculators where you can take into account the whole geometry of the transmission line, so not only of the signal trace, but also how this is positioned in respect to the return reference plane. And my recommendation here is to actually ask the manufacturer of your PCB for the corrected values, which are based on the PCB that you want to produce it, so based on the stackup that you have. Once the manufacturer tells you the trace width that you need to use based on your stackup, so in order to achieve the impedance requirement that you need, then you want to design the traces with this characteristic impedance. So for common signals, this is typically 50 ohms, but for more special signals, like the high-speed signal, you want to check that the requirements are for that specific protocol, because not all the signals, they need to have a 50 ohm impedance, but there are some variation with it. So make sure that the signals that you have to propagate requires a 50 ohm impedance or something else. But make sure that you know what is the impedance that the signals requires. So when we see that there is some change in the width of the signals, like in this case in here, we need to make sure that we use the same trace width, and when we do change, that this is actually justifiable, so that we know what we are doing, that it is made on purpose and not just by a mistake, or because we want to try to fix some other issues with that. Because what is most important for the signal is the impedance that it sees at each point in time of the transmission line. Otherwise, what will happen in this case is that the signal reaches this point and then it will create some reflections depending on the impedance mismatch that we have created. So impedance mismatches are very important and something that we have to keep in mind. And so without making this as a complicated matter, we have to remember that the impedance is simply the ratio between the voltage and the current. So if we change this ratio, we are directly alternating the signal, because if the ratio changes, so if the impedance changes, either the voltage or the current has to change. The next section that we need to analyze is the power section of the board. And the scope of doing this is mostly to make sure that the design uses the space around the converter efficiently as to minimize the current loops. So one of the biggest issues with power converters is that often the current loops are large, which will make them into antenna-like structures. And the problem with switching converters in terms of EMI is that in order to be as efficient as possible, their switching time has to be as fast as possible. So when this is the case, the amount of energy that needs to transition from high state to low state or vice versa is all compressed in a short amount of time. And this means that in this short amount of time, we will have many harmonics of the signal that construct this sharper transition. So what this also means for us is that now we are not dealing with one frequency component, which is the main switching frequency, but we are dealing with the main switching frequency plus the whole switching frequencies which form this sharp transition time. And this means that the chances for any of these frequency components to radiate based on the structure that we designed is much higher as well. So we have to be careful that our structure is designed so that it contains the sphere and not the opposite. And as I talked about it in the radiated emission video, the larger is the current loop, the larger is the emission. So we need to make the current loops as small as possible. One effective way to do that in a power converter, like a switching DC-DC converter, but the same applies also for the AC-DC converter, is to have the input and the output loops as small as possible. And this typically means to bring as close as possible the capacitors, either the input or the output capacitors, depending on the topology, also the loop that the inductor and the diodes form. So on this design, we can see that the capacitors are placed from the top layer. So before we propose an improvement to the client, we should understand if also the bottom layer can be used to place some components in that or not. And then, of course, if they tell that the bottom layer cannot be used, then we need to be able to bring the capacitor closer to the pins on the top layer. And if this is not the choice, then we need to see how we can improve this path between the component and the pins of the converter. So that we need to reduce this loop and also to reduce the inductance that is formed between the component and the pin. And the same thing applies to the processor. Actually, the processor is one of the important ones because its own power delivery network depends on it. So we want to make sure that the coupling capacitors are placed as close as possible to the pins to which they connect. The idea is in here to reduce as much as possible the inductance. And so this means that we have to take a look at the current path, not just how close it is to the pin, but what is the path that it takes from the component to the pin and what is the inductance in between. And usually what happens is that sometimes we move the capacitors on the other side of the board, but now the distance is closer, but the inductance is actually higher, depending on the vias and the traces and all the paths that it has to take. So we want to optimize it for a small inductance path and not just the distance. So don't focus just on bringing the capacitors closer to the pins, but actually focus on the path that it takes between the component and the pin. And I've covered this more in depth in the PDN lesson that you will find in my channel as well. Alright, so for the top layer, it seems to me that we have already covered enough improvements already. So we can take a look at the second layer. And as I said before, this layer looks pretty much as I would like it to be. What I will improve in here is actually the space between these vias so that they can have more copper filling in these areas. Otherwise, what you're doing in here is creating these gaps in the plane where no current can flow through it. So these will make the loops of the current a little bit longer, affecting directly the emissions of the traces on the top. To know how much they will have an impact there, we will have to simulate them. But still, since this is not a complex strategy that we can apply, I would rather improve it anyway. And other than that, the plane has no cuts, no split, or call it the gaps under the traces on the top, which created this impedance and discontinuities that we've talked about. So this is exactly what we want to have right here. And an identical plane, I would like to see also on layer 5, but as we saw, the design chose differently, so we will have to see what we can do with that. Let's now move to layer 3. So this is a bit of a mix, and we have these large copper fields in here, which covers the entire board, and then we also have some high-speed traces. So as I mentioned before, this can be better used for signal. So I would have moved some of the signals that we have under the layers and routed them in here. Also, the recommendation I gave before regarding the serpentine and the space between the traces applies in here, of course. So what we can do is we can pulse a bit more the traces here, especially considering meaning that if I remove this larger copper field, I can use the space of the board now much more efficiently. And the other point is regarding the traces here, which are pretty long. So when designing the traces, my goal should be to make them always as short as possible, so that the current loops are small and they don't create emission issues on my frequencies of interest, which are typically the one of the EMC test, but also of the signal bandwidth. And another important remark that I have here is that I already mentioned it, is that I would like to see more stitching vias connecting to these copper fields to the return reference plane on layer 2. And so like I said before, this will make the planes equipotential to each other, but also what happens is that the resonance now in between these two planes will get higher frequencies because of placing much across the vias between each other, so the resonance of this cavity there will get higher. And this is a good thing for us because we don't want to have resonances between these cavities at lower frequencies, otherwise we will see them later on in the EMC test. So by placing more stitching vias, typically this is 1/10 of the wavelength space between channels of the highest frequency component of the board, then would be quite effective because after the 10th harmonic, we start to lose quite a bit of energy. So this is not anymore relevant for us. But of course, this is a general rule of thumb, and you will have to evaluate based on what type of signals you have, what type of rise time you have, but also on how much it will increase the cost in terms of manufacturing, because adding more vias, so more holes, we increase a little bit the price of the board. So you just have to make sure that everything is between your capabilities in terms of manufacturing as well. So this is usually a trade-off. And nonetheless, increasing the number of stitching vias will help us towards the direction that I just mentioned of improving EMI. Now let's move to layer 4, where things get a little bit more complicated, because here I have a mix of signals. So I have digital signals, power traces, then these copper fields. So the first thing I would like to do is to remove completely these copper fields to have an idea on how much space this is actually taking from routing the space of the board. And we can see that once we remove the copper field, we still have quite some space where we can improve this layer. The major problem also that I see is that the traces are routed very close to each other, so we will have to increase the space between them in order to avoid the crosstalk. Also, what I don't really like in here is that we have these power traces routed very close to the signal traces. And so this can be a problem, especially in terms of conducted and radiated emissions, because any noise coupled to these thick traces can easily reach the cables and start radiating. But also the opposite can happen, where if the sifting of the cables is not done properly, we can have a immunity problem where the external interference now reaches the digital signals and interfere with the proper operation of the board. So what I would like to do in here is to increase the space between the power traces on the digital signals. And also in a situation like this one here, I would like to use the space available on the board so that the fringe fields of the signals do not couple with each other. And the same, of course, applies to these power traces here. So lastly, what we need to do in here is to increase the space between the traces to avoid coupling between them. And the same improvement that we mentioned before, also for the other layers, will apply here, of course. So we're not going to repeat them each time. Now moving to layer 5. As I mentioned already several times, this layer here, given the stackup, should be dedicated exclusive for the return reference plane. So this should be an exact mirror image of the layer 2. So here we will have to decide if to add 2 more layers, one between the layer 4 and layer 5, and then one between the layer 5 and layer 6, or if we will have to route the board entirely differently in order to keep the stackup. So since I saw a little bit of space on layer 3, maybe one of the things that we can do in here is to route the digital signals from layer 3 to layer 4, and then use layer 5 with their power to layer 3, so that the layer 5 now can be used as a full return reference plane instead of a power plane. If we can do that, we don't need to increase the layer numbers, and we can actually keep the cost down, still achieve some great results. Also here on layer 5, the plans used need to be justified. In other words, I need to make sure that really I need a plane in here instead of a power trace. So we have to check if the current requirements as well as the impedance requirements, they can only be fulfilled if I'm using the planes instead of the traces. Because if this is not the case, then I will remove the planes and route the power with the thicker tracks based on the power requirements that I have, of course. And the other reason why I want to replace this layer with a return reference plane is because the signal on layer 6 and on layer 4 are continuously crossing the splits between the planes. And this means that we're going to have the field propagating between these gaps, and the route that the return current that now has to go through for it to come back to the source is much larger. I've already mentioned that this is already related with the emissions that we have from the board, because the radiated emissions are directly related to the size of the loop. So this is exactly what we need to improve, and the reason also why we want to have a solid return reference plane with no gaps, splits, or any other impedance discontinuities that is going to break this solid plane. So layer 5 has to be modified for sure, and we have to choose one of the solutions that I already mentioned. So either we change the stack up and we use a 8-layer board, or we change the layout and we can maybe maintain a 6-layer stack up. Now let's take a look at the final layer. So this is layer number 6. Again, what I will do here is to remove the copper field to see how much space there is really on this layer. So here we have as well a lot of space that can be used. And again, the programs I see are still the same as before with the other layers. So there is a space to close to each other. So there is longer than necessary. And really the space of the board could be used much more efficiently. Also, what is good about this layer is that we don't have many components placed from the side of the board. So we can use more space for routing on the top layer, where the components then take the majority of the space. All right, so we covered the basics of conducting an EMI project review of a printed circuit board. And of course, there is much more involved, but I wanted to give you an idea on what it consists of and on how quickly you can identify EMI issues just by reviewing the layout. And if you're interested in becoming an EMI specialist yourself, you can head over to our website, fresioelectronics.com, where you will find the details on how to apply for one of our exclusive programs designed to help you do just that. So that's all for this video, and thank you for watching.